All right, so these are the 23 definitions that we want to make sure that we go through each one of these words and get a breakdown of what each of these are. All right, some of these words you might recognize as far as words go, but they sometimes mean things a little bit different to us. Like obviously you see the word garage there or bathroom, but this has to have some kind of defining sort of aspect to it. Everything, as I was saying yesterday as we were closing up, everything can't be a bathroom just because there's a sink in there. So there are some conditional things with these definitions, so this is why we're going to be going over them. So let's go to the first definition that we have. Now, for some of these, there's going to be 2 or 3 follow-ups to the single definition. So here again is where I'm going to be asking you guys to highlight. And if we come over to accessible, then as you guys can see, as I was saying, there are 3 different ones. So we're going to go over all 3. Make sure that you've highlighted at, again, if you want to highlight the entire definition, all good. If you just wanted to highlight the heading itself or just the word itself, then that would be fine as well. This is one of those where I think just the word itself that we're covering is enough. So there's three types of accessibility for the code book, and this falls into play when we look at electrical components, when we're talking about things that are live, right? Electricity that's energized that people can potentially get hurt with. And this is also me being able to get to these things. All right, so this is why there's so many accessibilities or definitions of accessible. So let's go through them. The first one says capable of being reached for operation, renewal, or inspection. So this would be, as applied to equipment that it says there, for example on that one would be like a fire extinguisher, where the fire extinguisher needs to be capable of being reached for operation. Right, so fire extinguisher needs to be accessible. What does it mean to be accessible for a fire extinguisher? Again, I can reach it so I can operate it, and they can do inspections on the fire extinguisher, and you can renew the inspection labels that they have on them. Now, I'm just using fire extinguisher as one of those things. This happens for other pieces of equipment as well, but that's what it means. So in other words, this equipment can't be up in a ceiling somewhere or too high where for you to grab, let's say again, use the fire extinguisher as our example. For me to get this fire extinguisher, it requires me to bring over a ladder and then get on the ladder and then be able to get the fire extinguisher. Obviously, this is not how we run those things. So that would be not capable of being reached for operation, as an example. Now, the second one is applied to wiring, all right, or wiring methods. Capable of being removed or exposed without damaging the building structure or finish, or not permanently closed or blocked by a structure or other electrical equipment, and etc. So let me pull up an image here. Again, I'll be trying to show you some images for a lot of these, just given the fact that some of you might not have seen these components yet. So 1 second. So let's take this for example. All right. Again, what does it mean to be accessible when I have some wires? So what happens a lot of the times with our wires is they don't just get tied to a machine, right? Or for example, the outlet. The wires land on the outlet, but that outlet gets mounted into a box. All right. We call this a junction box. There's a bunch of different names that the trade will use. Like in Florida, we used to call it a 1900 box because that was the catalog number for it. In New York, when I worked there, they called it a 4-square box. This box looks like this, right? And this is Grainger, which they're a supplier of these parts. And you can see here, they simply just call it an electrical box. All right, Rayco is the manufacturer for this box. This box is made out of steel. Here is if you were to measure this box, it is probably not 4 by 4. It's going to be like 3 and some change, right? But this is what we mean by nominal or trade size. This is a 4 by 4 square box. So the idea is this box has these little knockouts there, right? This is where we bring our conduits into this box. Now, of course, they get securely fastened into this area. And then there's a little screw up top here and a little screw down here on the bottom, because along with this box, they sell a cover for this box. Different style, like for example, for the outlet, it would be something like this one right here. This is what we call a plaster ring, and this is where on that little screw there and the one right below it, this is where you would mount your outlet. If you've never seen behind an outlet, which when I started the electrical trade, I had not seen behind an outlet yet. Nobody had opened up an outlet for me. There was no one in my family that did electrical, and nobody wanted me to do electrical because they were scared of it. So everybody was scared of electricity back in the day. I think it's getting easier now with all the low voltage systems and wireless systems that everybody's using. But back in the day, it was very scary. This is just to show you another cover for this box. This is called a blank cover. All right, it's called a blank or just blank cover. And this is for when there isn't going to be an outlet in that box. We're just going to splice some wires together. In other words, we're going to bring some wires together to continue the electricity down to another box that may have an outlet or whatever down the line. And so when we splice, we cover this box. All right, we have to cover all of those splices up and keep everything wire-wise contained into that junction box. All right, I think it's pretty universal to call it junction box. Again, some people Foursquare and some other names. I think junction box is pretty universal. So now just kind of going back to this definition of accessible as it pertains to wires, that's what they mean. When I splice those wires and I cover that box, again, there's no outlet there. I just spliced wires and I covered that box. The next electrician needs to be able to, as it says here, capable of being removed. In other words, you should be able to remove the cover, expose those wires without damaging the building structure in any way. One of the big ones with this is you are not allowed to bury these boxes behind drywall. And people try all the time. All right, they just try to put a splice there, bury it behind that. This happens a lot of times when, for example, there's a switch on the wall. Excuse me, I just take a page here. All right, person might have a switch on the wall, right? Little on-off switch setup. And then they get rid of the switch. And then they move the switch somewhere else. But the electrician has these wires in there, right? They're just in there, and these wires are in there as well, and they're all spliced with the little wire nuts that we have and spliced in there as well. So now you have a choice. What do you do with these wires? Well, the correct thing to do is they still need to be accessible, even though you move the switch down the line or somewhere else on the wall. Because they're wires, because they're spliced, I still need to be able to get to these wires. In other words, you're not just allowed to put drywall over this. Bury the wires into the junction box. We don't really need them for anything ever again. And just put some drywall over it, and it's like they're never there. All right. Unfortunately, instead, you're supposed to put a blank cover, like the one I showed you in metal, but if it's on the drywall, they're usually plastic and white or whatever color the other outlets are. You might have seen these before. They get screwed into the box, blanked over. Now, the only thing is you have this blank cover on the wall, and some people don't like it. Right? It's aesthetics, why they might just bury it behind drywall.
Question, Mr.
Yes.
Perez, would that be a code violation?
That is 100% a code violation, yes.
Okay. Yeah, I had a cousin who had bought a house. I think it was a fix and flip, and I had a friend that came in to do the. I think he was installing a TV, and he was cutting through the drywall, and he ran into.
One of these.
Yeah, he ran into one of those behind the drywall, and he just. I think the wire was live too, so he almost. Yeah, so I was curious. Like, I was assuming that was a major violation.
Yeah. one of the main reasons is something like that, where somebody could be, unknown to the fact that there's wires behind there, is just cutting through the drywall or whatever, mounting some, and then you're hitting some live wires. That's one of the possible. The other one, again, what if you have one of these wires gets damaged, this wire nut comes off, age starts to become brittle, the wires, and you have a disconnection of the power there. Now, just to access these wires, you're going to have to, one, find it, because the electrician that did this is gone. No one's ever going to find that person again. Your friend, you say, buy a house. Who was the electrician? Nobody knows that. So no one's going to tell you, hey, there's some wires buried behind the walls. This is a discovery made. So now, how does this become illegal, right? There's another little bit of, is it illegal? Yes. Do people do it? All the time. All the time. Have I done it? I won't tell you that.
Yes.
Do people do it? All the time. However, yeah, if you do get caught with something like that, one, you fail inspections. But remember, that is only as the building is being built. If you were to do some work in someone's house, as I was mentioning yesterday, and you bury some wires behind there, no problem. Bye, no inspector, no one's going to come see things. If, like just happened to this person, somebody or friend of the student that was just mentioning that, someone gets hurt with those wires that you did that, you are 100% liable. So that's why we try to do things as close to the code as we can. No, 100% code compliant as we can. So this is a big one with wires. People try to bury them all the time. They have to be accessible, all right? Actually, this is another one that happens, and not so bad, but it is still a problem. So, for example, and this is for the in-person students because you guys have this. If you guys look up right now in the classroom, and you guys have seen these before too online, it's called a drop ceiling. All right, the ceiling is a drop ceiling because it has little ceiling tiles up there. And you can pop open that ceiling tile, just get it out of the way, and access that area of the ceiling. It's called plenum, if anyone is curious. Plenum ceiling. It's the area between the drop ceiling and the actual concrete that's up there. And they run wires there, and the air conditioning ducts run through all of that. That's accessible. You can have junction boxes up there. Because for me, to get to one of these junction boxes, I can pop open the ceiling tile. Now, did this say that I had to be able to reach it? No. It just said, if we can read it again, capable of being reached quickly for, excuse me, I'm reading the wrong one. Capable of being removed or exposed without damaging the building structure or finish, or not permanently closed in, drywall, or blocked by the structure. Maybe somebody puts something in front of this now and we can't access it. Now, if it's a machine and it's movable, sometimes this is okay. Other electrical equipment, and if you can't mount something electrical on top of something electrical, or any other building system or finish of the building. So, again, the drop ceiling above you, even though I have to go get a ladder because I'm not that tall, and then climb up the ladder and pop open the ceiling tile, then I can reach the junction box. That fits this code requirement. All right? We're going to read another word now that becomes a little bit different. And I was just starting to read it. That's why I said, oh no, I'm on the wrong one. So wires, now what happens, let's say for example, if a building clears out that drop ceiling and then puts drywall right where you're at. Now this is no longer accessible anymore. All right, it can't be permanently closed in and it can't be blocked. So keep that in mind. This is a lot of times why people have to cut in. Maybe you've seen these in buildings or so before, and they have just a little door up on the top that they can open up. All right, the little door opens up, and now they can access all of the things up in the ceiling. And sometimes you see this in the middle of a drywall ceiling. The ceiling is completely drywall all the way around. There's no real way to get into any of thing up there. but they have one of these little hatches sort of somewhere tucked away. Now you can pop that open and crawl up in there, and I've seen this be argued on a job site as to whether or not the inspector feels that there is enough accessibility to junction boxes and other things that have wires in them. Now, a lot of stuff goes in these ceilings sometimes, and things get closed off in a way that contractor thinks it's not closed off. Inspector's sitting there going, I think that's closed off. And now they're just trying to figure out who's right or who's wrong. Remember, and we'll get to this definition here, authority having jurisdiction is always right. But all right, now the third one is readily accessible. All right, that's why I said there's a different one. Readily adds another feature to this. This one is being capable or capable of being reached quickly for operation. Like, let's say, for example, a stop button to a machine so that you can stop that machine in case of an emergency. This has to be readily accessible, meaning quickly. All right, readily accessible for operation, renewal, or inspections, again, without requiring those to whom ready access is a requisite. So in other words, the operator of the machine needs to be able to reach that stop button without any kind of issues. However, other than keys, the person can have something locked behind something that they have a key to. All right, but the only thing it should not require is tools. In other words, me taking apart an access door where for me to stop this machine, I have to get in there and unscrew and unscrew and unscrew and take off a cover and then press stop. This is not readily accessible anymore. So a tool cannot be used, a key can be used. So I would say, if I was highlighting, that's a point that I would like to highlight there. All right, and except for the first one, because I think it's just such a short sentence, not really needed, there might be something within the other ones that you might want to highlight. Like, for example, permanently closed in. This would be a feature of accessible that I would want to stand out for me, because that's the main point here from that accessible, is that the junction boxes, the things that have the wires connected to each other, has to be accessible in a way that it does not end up being permanently closed in. And then you can reach for the other ones like blocked and other, all these. But that's the main point of that definition. All right, the main point of readily accessible is really in the name. So that's why I said maybe something here that I would point to is a tool cannot be used, a key can be used. Right? That would be, if you were a teacher, that would be a good question to ask. Can I use a tool? Yes or no, or true or false. Set it up like that. Can I use a key? True or false? Just to make sure we know the difference between those two actions. All right? They are not allowing us to put a tool to the application of readily accessible, but a key can. Here again, can't climb over something. So now going to grab the ladder is not good. For the one before that, grabbing the ladder was fine for regular accessible. For readily accessible, as it says here, cannot. All right, without. Being requires those who are ready, whom ready access is a requisite. Such actions as a tool, climbing over or under something to remove an obstacle. If I have to get something out of the way before I can access this, or to resort to portable ladders and other going, grabbing a ladder, and now, in other words, I can't put the stop button, just as an example, because I was using it earlier, in the drop ceiling, even though it has wires and connections. But the fact that it's in a stop button to a machine now makes it that it has to be readily accessible. All right, just to give you some examples of these definitions. They have a ton of different ways in which they show up. These are just some main points that I've seen before too, and noticed from job sites and things like that, where I've seen these things come into play. I saw that one accessibility of the wires argued in a lobby of a building once. There was an access door, but if you looked inside that area, yes, you have enough room to crawl as a human, but there was an AC duct, right, running through the whole thing. So you can't get over the AC duct. But the contractor was like, well, the AC duct's not my problem. It meets the code. And the inspector was, I'm not having it. That's where it ended up. That's where it ended. All right, so one word, accessible, out of the way. Let's go on to the next word. Still on the same page, just adjacent, ampacity. All right, I'll read this, and like I said, I'll unpack the words a little bit just to give you some understanding of things. There might even, like I said, be a little bit of math to some of these. Ampacity is the maximum current in amperes, which I will always just from this point forward call amps. In other words, current in amperage, because whenever we get information on anything that's electrical, for example, if I grab a light bulb, it doesn't say what the current of the light bulb says, or is rather, it says what the amperage of the light bulb is. So that's why it mentions that. Current is how we approach it with Ohm's law, right? We do P over E equals I. I is current. We don't say I is amperage, just some terms. They mean the same thing, essentially. There is some differences, but same. So, coming back, the maximum current in amps, so the maximum amperage that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. So a little bit to unpack there. All right. So what this is basically saying is how much amperage a wire can carry. Now we have a lot of different wires. We're not getting to that yet. We'll get to that when we get to Article 110. But I'm going to skip ahead a little bit to when we do get to Article 110 and show you this particular table. All right, this particular table, and you don't have to go there right now in the code book, is called Table 31016. All right, and let this come up for 1 second. It looks like this. I'm going to zoom in on that a little bit better because right now it could be a lot blurry. So let me reshape this. All right, let me get a little bit closer to it. And we'll go over this a little bit or more I should say, when we get over to Article 110. But these are all of our wire sizes, or what we call wire gauges. All right, that's what that G right there stands for. It's called American Wire Gauge. That's the system that we use to gauge wire, just like you gauge metal. If you've ever worked with sheet metal, it has gauges as far as the thickness of that metal. So all of these numbers here on the side represent the thickness of each of the conductors that we have. Not this section over here. All right, the gauges are just these right here. All right, and don't worry about the numbers. Some go, as they get bigger, the number gets larger here, but then it goes in the other direction. So the only thing you really need to know, if you wanted to know something right now about it, is just the wires get larger or thicker as far as gauge goes as we go down this list of conductors. All of this information here is the amperage that each of those conductors can carry. All right, so going back to that note here, the maximum current in amperage that a conductor can carry continuously, meaning if you were to leave this load on or this machine on or the lights on for 24, 36, or however many hours it takes continuously, under the conditions of use without exceeding the temperature rating. All right. So just one more time, these are the conductor sizes. This that I have squared out in blue are the amperages for each individual conductors, but you'll notice there are 1, 2, and 3 columns. because each of those columns has a different temperature rating for the insulation around the conductor. All right, you guys have all seen a wire, I assume, and you notice there's a little bit of plastic around the wire that does not let us touch the conductor, the conductive part, whether it's copper or, oops, sorry about that, I meant to grab the pen, or aluminum, or copper clad aluminum, which is just basically aluminum with a little bit of copper painted on it, or clad heated onto it. And these are a bunch of insulation types. And so all this is telling us is that this column is rated for, and we always use Celsius when we describe these. Again, you don't have to really write any of this down. We'll get into more of this next week. Or actually, 110 we actually get to, I think, tomorrow. So tomorrow we'll be going over this again in broader detail. This column is for wires rated with an insulation of 75 degrees Celsius, and this one is of 90 degrees Celsius. And what you'll notice, and let's just pick one wire, we'll do more of this tomorrow, as I said. Let's, for example, pick this number 8. In the 60 degree column, the number 8 can hold 40 amps. Should be able to see that? Yeah. If you go to the 75 degree column, that number 8 now holds 10 more amps, a little bit more amperage. And if you go to the last column, the wire can now hold, or the conductor can now hold 5 more amps. So you've now seen a trend. As the insulation temperature rating goes up, the wire can hold more amperage. All of this is sort of just related to each other. Amperage is heat. Heat is going around the wire when there's amperage on it. The insulation is dealing with that amperage, along with the fact that it's inside of a conduit already bunched in with a bunch of other wires. They also have amperage. There's just heat everywhere around everybody. This heat that's in there affects the wire's ability to hold amperage. So the wires can also effectively lose their ability to hold the amperage that is said to be able to hold if we start to put too many wires into a conduit. There's a whole section that walks us through, and you'll get to that in code B, where you'll size wires, and then you'll be given some adjustments to make for those wires that you are sizing based off of temperature around the wires and how many wires are in the conduit hole, etc. to this particular article. But it starts here just with a understanding of that word, ampacity. Ampacity again means a conductor's ability to hold amperage. So when I say that number 8 has an ampacity of 55 amps, I am telling you that that number 8 has an ability to hold 55 amps. All right, 1 second as I get back to the lecture where we're at. All right, so that's what it means to, or that's what the word ampacity means. All right, the next word that we'll look at is authority having jurisdiction. We already went over this one, but just make sure that you have it highlighted in the section. Authority having jurisdiction is the inspector that they sent out to a job site and try to make sure it's on page, oh yeah, bottom right of page 27, way down here. Authority having jurisdiction. Sometimes you do see it abbreviated to AHJ, the way it says there. An organization, office, or individual responsible for enforcing all of these code requirements. Inspectors, just to unpack that a little bit as we go on to the next word, they do come in different, from different governing bodies. For example, you know, everything gets sort of zoned differently. You can have a house that is zoned to the county, so you have a county inspector, and then you get zoned, your house now sits in another area, and it's zoned to the city. For example, we have that here, where I'm at in Chattanooga. All right, if you are 10 blocks over that way, you are zoned to the county of Red Bank. Where my house is 10 blocks over here, I am zoned to the Chattanooga city. Meaning, and this is why that's important, is sometimes counties and cities have extra information or extra rules to what they want to see applied in their city. I remember in Dade County where I started my electrical time. Dade County, Florida. All right, so we have a county of Dade, and on the other side we have the county of Broward. And you had sometimes a building sitting here and a building sitting over here. The county of Broward, I actually don't remember who, but I do remember there was a difference between both of these. The county of Broward required fuses. All right, it requires fuses for all of their light fixtures. Across the street, this other building, the county of Dade, did not require fuses on any of the light fixtures. So if your house sits on one of these, fuses in your light fixtures. If your house sits on the other one, no fuses in the light fixtures. So this is why you need to know who the authority having jurisdiction is for your job site, because the code sets the standard. And take this with you now and remember this. I don't think we need it for a note because this is not going to come up here. But the code sets the standards. The building codes supersede them. The building codes are given by, like I said, either county or city, or sometimes it's called a municipality, or whatever the case may be. So you always have to then check your building codes when you're going to build. Because sometimes, and this happens when blueprints get designed somewhere else, in another state, doing the blueprints for the Walmart that's being built over here in this other state. And they're not familiar with the building codes of that county. And you can fail an inspection. It's usually not massive, not something that's just like, oh my God, how can you miss that? But it's just that little thing, like we forgot fuses in every light in this building. That's a nightmare situation now, because we're going to have to now put fuses in every single light. So, it could become a nightmare. So you always have to check those building codes. And the last time it hit me was back when I lived in Los Angeles, and I was going to go work, and I did go do a service change, like change the panel and change the pipe, or, the conduit that goes up to meet the utility company's wires. I did all of that. In Joshua Tree, that conduit that leaves the panel and goes and receives the wires from the utility company, it has to be a minimum size of 2-inch. Even though, if I use the code book, for the wires that I was putting in this conduit, the conduit only needed to be 1.5 inches. So the code book was allowing me to put a smaller conduit based off of the code book, but the county or authority having jurisdiction supersedes that. So always remember that. Won't come up in your electrical career just yet, but something to consider. By the way, is anybody having any follow-up questions as we're going through for any of the words that we've gone through so far? Again, feel free. Yes, there was?
No.
All right. All right, let's go on to the next one. Exactly, bathroom. Now, not too complicated of a situation, but there is a definition. So here I would try to highlight at least something along it. Again, if you just highlighted bathroom, it would also be fine because not that big of a paragraph. But this is how a bathroom is defined. So as I was saying yesterday when we were wrapping up, if there's just a sink in there, or if you just have an area in the garage where you have a shower, or by the pool area, there's just a shower head, so somebody can, shower off before they go into the house or whatever the case may be, this is not considered a bathroom. So a bathroom is, as it says there, an area including a sink with one or more of these. So first there has to be a sink, then there has to be one or more of these other ones. And you guys have all been in bathrooms, I assume. So you've seen this situation, and you've seen now why we can label, like, let's say, for example, in a house they have a sink and a toilet, no shower, so they call it a half bath. This is a bathroom. And again, the reason why you want to know if this is a bathroom versus not a bathroom is that there are codes that follow up with the definition of a bathroom. Has to have this type of outlet in there, must have this minimum wire size, etc. Things that can't be in the bathroom. By the way, you can't have the electrical panel in the bathroom. You can put it in literally any other room in the house. except for the attic because it has to be readily accessible, by the way. But you can't have it in the bathroom either. So you want to know what a bathroom is defined as because, again, follow-up code sections could present a problem. All right, sorry about that before we finish that one up. And again, if there's any follow-ups, I don't know if there's any follow-ups with bathrooms, so I assume not. So let's jump over to the next one, which is branch circuits. All right, and here again we have 1, 2, 3, 4. There are a bunch of branch circuits, so let's go through all of them quickly because we really just have to hit the first one that defines it, and then the rest of them piggyback onto that. So the first one, which we should highlight here, is branch circuits in this definition, the circuit conductors between the final overcurrent protection device protecting the circuit and the outlet. Oops, sorry about that. Meant to switch over to this camera. So what does that mean? It means, well, it means literally what it says. It's the wires that leave the final overcurrent protection device. So an overcurrent protection device is a breaker or a fuse, but in the beginning we really just focus on breakers. All right, and as you know, breakers, or are getting familiar with, I should say, breakers live inside panels. We have our little breakers of different sizes, 15 and 20 and 30 amps and etc. These will feed an outlet. For example, all right, the outlet also has a neutral, but we're going to worry about that right now. But here's the other thing. Sometimes inside this panel, there could be a larger breaker that feeds some wires over to, let's say, a sub-panel inside the garage that takes care of the garage equipment, right? Has some outlets inside the garage. So these wires here would be considered branch circuit, but these wires here are not considered part of the branch circuit. These wires here are what we call feeder wires. You don't have to write this part down, but just so you understand what the branch circuit is, because they are feeding power to a panel, and now these wires leaving that panel and going to an outlet, this would again be considered a branch circuit. So going back over to that definition of what a branch circuit is, it's the wires that leave the last overcurrent protection device, the last breaker, and then end up at an outlet. Not like, again, for example, the wires that left this breaker and ended up at another breaker, because there's a breaker inside this panel waiting for those wires. Now, you'll get more into that definition in Article 210, which is only on branch circuits, and there you'll get a better definition of it. But for now, that's how you should understand a branch circuit, the wires that leave the panel and end up at the outlet. All right, that would be considered a branch circuit. These are the wires that are branching out of the panel and going into all the different circuits throughout the house or building of any kind. Now, an appliance branch circuit, and now these will just be easy to follow up with. An appliance branch circuit is one of those circuits that left the panel and ended up at an outlet that's going to service an appliance. Like, for example, a washing machine or a dryer or the oven. I'm trying to think of some other ones here. Not appliances, like, for example, not appliances like the blender that I bought or the toaster that I bought. Those do have a name. They're called small appliance circuits. They are requirements when you're building a house to have some small appliance circuits inside the kitchen to provide power for those things that people will buy. Like, again, blenders and toasters and things, like somebody buys an air fryer, somebody else doesn't have one. So there isn't an air fryer outlet. There's just an outlet provided for small appliances. An appliance branch circuit is not small appliance. So appliance branch circuit is the larger appliances, like refrigerator would also be considered one of those. And again, dryer, washing machine, etc. So we have those branch circuits as well. General purpose branch circuits would be outlets, as it says here, a branch circuit that supplies 2 or more receptacles or outlets for lighting and appliances as well. All right, the appliance branch circuit, just to read that definition, that supplies energy to 1 or more outlets to which appliances are going to be connected to, and that has no permanent connection to, and this will for now just be lights. We will look at this definition and get a better understanding of it. But your lights that are not part of the appliance. So the appliance branch circuits cannot feed lights. The general purpose branch circuit, for example, you could plug an appliance into one of these, but there will be lighting and other things connected to this circuit as well, or allowed to be connected to this circuit as well. So for an example of a general purpose branch circuit would be the wires going to a bedroom, where who knows what the person's going to plug into their bedroom. It could be an appliance because somebody could have a little mini fridge in there, so appliance. But most likely there's going to be a lamp, computer, or something like that. So that would be considered general purpose branch circuit. So when you're staring at a panel, all this will eventually start to tie in when you go through building one of these together with the code sections that go with them. But when you're staring at a panel and you got all these different breakers, and if you've been staring at them going, what are all these breakers for? This is what they're for. Therefore, some of them are for appliance branch circuits, some of them are for general purpose branch circuits. Some of them, like the next one that says individual branch circuits, a branch circuit that supplies only one utilization equipment. You'll see this word used throughout the code book. This is a way to reference things like the central air conditioning unit, or if you were now talking about a restaurant, well, refrigeration units. Utilization equipment are things that we're going to use that are larger than appliances. They're not movable, they're not anything like that. They're just fixed large pieces of machinery in most cases. But one easy one to understand is the air conditioner, which is in every single building. So one of the breakers inside the panel is feeding the air conditioners. The next one is motor branch circuits, and these, as it says here, the conductors or wires including equipment between the motors, right, between the overcurrent protection device and the motor itself. The thing that protects the motor, short circuit or ground faults to an individual motor. So now, obviously, a lot of these aren't in some panels, like maybe there's no motors inside of a residential panel. There might be, if they have a garage, they have a garage door motor, but that one doesn't have an individual. But this is more for industrial machinery where we have a lot of motors on all the manufacturing machines. And so if you're standing in front of a panel in an industrial setting, you got a lot of these large breakers that you'll see in there, and they're motor branch circuits. So now you have an idea of branch circuits. The last one is a little bit confusing because I really didn't explain what a single branch circuit is. But now they're jumping into multiple or multi-wire branch circuits. So let me explain that one for a little bit because this will be necessary for you guys to also understand. It's going to come up along the way in other code sections as well. So we have panels and we have breakers inside the panels. Now let me show you a couple of breakers so you guys get an idea of the types of breakers that we have out there. All right, we have single pole breakers that are just going to have one single wire connected to it. All right, this is generally the ones that are going to outlets and lights throughout the house. A single pole breaker. Now, some of the bigger pieces of equipment, let's just keep to a house because I assume everybody knows a lot of the things that I'm going to talk about. Like if I'm talking about three-phase motors or something like that, people might not have seen these yet. So it's better to kind of stick to things we know just in the beginning. So let's say, for example, the dryer. The dryer is a larger piece of equipment that requires 240 volts. And so you have a 2-pole breaker, and there will be 2 wires going over to that dryer. Or we'll just say L for load. Now, when you get into commercial and industrial buildings, there is 3-phase systems. And here you'll have a 3-pole breaker. And this is a breaker that has 1, 2, and 3 wires leading to a load. And in most cases, those loads are motors. It also could be, again, machinery in some other way that's not using a motor. Mostly everything uses a motor, but there could be something that heats up water or etc. Moves a crane or something like that. But usually there's a motor attached to that. So a lot of these 3-phase systems are motor loads. That's why it has a whole motor branch circuits. So going back to the beginning, this is a single branch circuit. There's only 1 wire leaving here. The neutral will follow along with it because the neutral for these single circuits will need to be part of energizing this equipment. The ground, don't worry about it. Yes, it goes everywhere, but it's just for protecting the system, not for running it. A multi-wire branch circuit would be this one. 2 wires, more than 1. And also to include the 3-pole breaker as well. Now, there is going to be some addition to that, but that's good for now just to get an understanding of it. So again, just because you're going to be seeing these things a lot more now, standing in front of panels and seeing breakers, and now you can make sense of some of what these breakers are doing. 1-wire breakers versus 2-wire breakers. It'll be a while before you see a 3-wire breaker, not until you get to the motors classes, but they're out there as well. So that takes us to the next word, which is circuit breakers. Let's run down over to circuit breakers. Like I said, there are a lot of words. Look how many cable things there are, from fiber optics to everything else. So let's jump all the way down to circuit breakers, which are going to be, just wanted to find the page, the bottom, well, the whole right side bottom, really, of page
31.
31. Thank you, sir. And we land at circuit breakers. Now we got a lot of circuit breakers here. I just showed you some different models and types. So first, let's read the definition of what a circuit breaker is. A device designed to open and close. This could be on or off, or that word that you'll hear a lot used called trip. When the breaker trips, T-R-I-P-S. And this means the breaker has, in the case of trip, it's just the open part, because the close part is when you turn on the breaker. This is a term that you should start to get familiar with. Open is off, closed is on, if you weren't aware of that. And the only reason we say that open and close is because some things are not turning on and off. Some things are energizing and de-energizing. Some things are starting and stopping. Some things are turning on and off. But the catch-all to all that is understanding open and close. So a breaker, circuit breaker is one of these devices that on-off, so we want to turn them on and turn them off when we want to energize the circuit and de-energize the circuit. But while the circuit is on, if anything happens to those wires or the thing that somebody plugged into or the outlet sitting there, short circuits and ground faults and overloads. All right, we'll get to overcurrent, which is all 3 of those things. Then you want the breaker to respond. All right, you want the breaker to trip and respond to that fault, as we call it. So going back over here, a device designed to open and close a circuit by non-automatic means, meaning physically has to be opened and closed, and to open the circuit automatically on a predetermined overcurrent, which is too much amperage in the circuit. But what does it mean to be too much amperage in a circuit? That depends on the size of the breaker. Some breakers are 20 amps, some breakers are 30 amps, some are 40, 50, 60, all the way up to 6,000. So if you have a circuit breaker, the amperage that's in that circuit and the amperage being carried by the conductors, by the wires, that amperage cannot exceed what the breaker is rated for. If it does, then again, the breaker is going to, in this case now, not non-automatic means. Now we want automatic means to do that. On predetermined overcurrent without damage to itself when properly applied within its rating. All right, that's why I was going into all those words, because they're going to show up here. Now, there is an informational note to that. Remember, informational note just means added information, not rules or anything. The automatic opening means can be integral, so inside of it. Direct acting with the circuit breaker, meaning something can automatically shut off the circuit breaker. There are relays that are set up sometimes to off something. Or have a remote way of being able to shut off that breaker. I will tell you, I've never worked with a remote setup that shuts off a circuit breaker in the event of a problem like a short circuit or a ground fault or overcurrent, but they are out there, like for example, gas stations have this. I've never worked with it, but if there's a fire at one of the fire pumps, there's an automatic shut off of all the breakers. All the power gets shut off at the gas station. All right, because, you know, gas and fire and all that stuff. So chemical treatment plant, what we call hazardous locations, will get some of these automatic shutoffs of the breaker during some events. So that's what a circuit breaker is. And then there's just a bunch of different types of circuit breakers. All right, the one we're going to focus on, because it's the one that we use in a general way, like this is every breaker that I've ever installed. And if you're in somebody's house or in your house or in a building, like the one you're in right now, it's most likely one of these breakers, which is this one here in the middle, I guess. Yeah, pretty much in the middle, which is called an inverse time circuit breaker. Now, nobody ever calls breakers an inverse time breaker. We just call it a circuit breaker. But just to go over the definition, then I'll explain a little bit more about the breaker versus what is the difference between the other ones. I'll explain. But to the definition, a qualifying term indicating that there is a delay. This is a big thing in our world. All right, a delay purposely introduced in the tripping action of the circuit breaker, and the delay decreases the magnitude of the current increases. Or of the current increases. Excuse me. All right. So let me unpack that a little bit, because here's something that happens. All right. So I got a circuit breaker, and you might have even seen this. And say I got it at 20 amps, and this circuit breaker goes to an outlet. Right, and let's say you plug in an air conditioner into this outlet. Now, when this air conditioner starts, there is an effect that happens to the amperage, because it requires sometimes a lot of energy when a load first starts to get things kind of going in the load. So an air conditioner, because it has to compress that gas, is one of them. Refrigerators are another one. One of the big ones are motors, and I'll get to the difference here in a second. But let's say, for example, when this air conditioner is on and running, its normal amperage that you'll measure in the circuit, let's say these are pretty high, but let's give it some numbers like, let's say 15 amps. Now, if you look at the breaker that's protecting this circuit, it's 20, so that's already good. And we'll assume that the wires can also hold 20, but you also want to do that. So everything so far is good. Except when the air conditioner turns off and then turns back on, there's an effect that happens on this amperage, which is called, and I'll write it here. Feel free to write this down if you want. You really don't need this information yet to like write down, but it's a good thing to know, because you probably, again, have seen this effect. It's called inrush current or amperage, but we mostly just call it current. I'll slide this over to the right, because sometimes, or left, sometimes you guys can't see there. What inrush current is for a second, let's say, when that air conditioner first turns on, or when a motor first turns on, this amperage of 15 amps skyrockets. It goes up. Inrush current. You have this massive amount of energy required to move the motor or compress the gas in that air conditioner, that this amperage goes up. Sometimes, with motors specifically, it can be 3 to 5 times that amperage down here. So for a second only, that 15 can become some pretty high numbers. All right, what's that, 75? So now look at how ridiculous this is, right? We have a 20 amp breaker that's about to deal with 75 amps for 1 second. Sometimes even a little bit more, especially when it comes to motors, because when they first turn on, not only does it require a lot to start turning a motor, because the shaft has to spin about 2,000 rotations per minute, so when you were not spinning, to go at 2,000 per minute, it takes a lot of energy. Now, you might also be at that exact moment moving an elevator full of people. So that little spike can delay a little bit. Now going back to this breaker. That's why this breaker has a delay feature. And that's why all of the general breakers that we put have this little delay feature. So that in the event when things first turn on, and you get this spike of energy, sometimes it's called the spike of energy. You can more so understand it because you guys are electricians as a spike of amperage. Then that breaker doesn't trip. Right? That's where it's featured at. A delay purposely introduced in the tripping action. So inverse time breakers, and you'll see different numbers here depending on what book you're looking at. Some say 5, some say 8 seconds. But that's about the delay. 5 to 8 seconds. These breakers are designed to hold off on opening the circuit in the event that amperage has gone past what their rating is. They give it about 5 to 8 seconds for things to temper down after they've started and after they've energized. Now, the reason why I said you might have seen this effect is maybe you've seen lights dim when something turns on. That is kind of that effect. As the amperage goes up on this one thing, the voltage goes down everywhere else, like Ohm's law says. All right, I'll pause there for a second. Does anybody have any follow-up questions to these circuit breakers? I will add something to this, which we're not going to talk about within all this. Overcurrent protection devices, as I said, there are 2 types. There's circuit breakers. There's also fuses, which are more so used on machines and utilization equipment. These fuses also have this same feature. In fact, more so than the breaker. By a few seconds, but more so. Now, this is one of those breakers. And now to the homework question. So there might be a homework question on some other breakers here, so you should be able to find the answers as well. But there is a complete other side to these style breakers. Not one that delays, but one that is instantaneous trip. A qualifying term indicating that no delay whatsoever is introduced to the tripping mechanism. So this one will trip the moment the amperage gets to 20, even for 1 split second. It's designed to what we call fast acting response time. It will trip instantly. So this is good for like a main breaker, like the main breaker that's at the panel. And then you have all of your little individual branch circuit breakers. Your branch circuit breakers delay, inverse time. Your main breaker, that's the one you want to have as an instantaneous. All right, just to give you a example of one of those. Now, there's some other ones. We'll ignore those. Just, I mean, not that I'll ignore them. It's just that these aren't really that popular. Like an adjustable breaker, one that you can adjust the amperage and the delay of the time. I don't see these as often. Same thing like a non-adjustable breaker. Same other side to this. All right, now the next term that we're going to look at is continuous load. All right, and here, as I said, we're going to look at some math. I didn't know if we were going to get to it today, but we will just because we've gotten to this, continuous load. Let me just find this one. Continuous load. It should be on page, and we should have found it, 34. Where we have continuous load. Very small little note here. There's only one feature to a continuous load, but it also requires us to, well, is there a is there a load that isn't continuous? So first the definition, a load, and remember what a load is, just again, reminders of these things, because we're just getting started. What is a load? Things that I plug into the outlets, the machines that actually turn on, the things that are energizing and de-energizing. So again, the load is not the outlet. That's not a load. The outlet just has voltage ready to go. You plug in a lamp, the lamp's the load. So there are loads that operate for longer than 3 hours. This is what this is saying. And what we call that is a continuous load, a load where the maximum current is expected to continue for 3 hours or more. And I would highlight that. I would highlight 3 hours or more, because that's the specific number. Not more than 3 hours, 3 hours or more. Those are two different things, especially when you're arguing law. If this note said more than 3 hours, then what is that number? A lawyer would argue it this way. What do you mean? 3 and 1 minute, or 3 and 59 minutes and then 4 o'clock? Is it 4, or is it, this would be a whole, so 3 or more. So they're really specific with that as well. So a load, something that you plug into the outlets, or that you energize or turn on, that operates for less than 3 hours. This is called a non-continuous load. All right, so I'll just actually add this to my note here, just in parentheses, because you don't see it over in these areas here when we start getting to these other letters. So just a reminder, it's just a load that only turns on and off for a few minutes or something like that. To give you an example, although this falls technically under a different term, but let's say the garage door motor. It turns on for a few seconds, opens the door, then shuts off, and then it's not running for 3 hours. Like lights. Lights are considered continuous loads. Also, it can be something as can operate for 3 hours or more. It isn't right now, but when we do turn them on, this thing is going to operate for 5, 6, 7 hours. And then I'll shut it off. So that's the effect of continuous and non-continuous. And there's going to be some future stuff in which, as I said, math will involve whenever you're dealing with one of these loads. All right, like let's say again, let's go to a for example. If I am energizing something and this thing operates at 15 amps when we turn it on. All right, the normal running amperage, or what this definition called the maximum current that is expected. So when I turn on this load, whatever it is, again, you can think of this as anything, a washing machine, a dryer, a air conditioner, a compressor, anything that I'm turning on. It's going to have a maximum amperage of 15 amps. All right, and this is a continuous load. And down here below, I have a non-continuous load. And this load operates also at a maximum current of 15 amps. When I go to consider, actually I'm going to change these numbers, and for a reason. I'm going to change them to 18. Sorry if you wrote 15 or if anybody's writing that out. Just 18, and it's going to be for a reason. When I go to get a breaker that is going to be energizing this circuit, I can't buy a 20 amp breaker for this. Even though, again, it does seem like I could, because that's 18 amps and this breaker is 20 amps. So it covers the 18. Yes, when this thing turns on, it spikes for a second, but remember, this is an inverse time breaker, so it can handle that. Because what the code is going to tell us, we're not doing this math, but I just want to explain where the continuous is going to come into effect. Just showing the math. And you can feel free to write this out. We're going to have to increase this by 125% first, which I believe is 22.5. And now the breaker that I have to buy is actually a 25 amp breaker, a little bit bigger than 20. So in this circumstance here with a continuous load, I would have made a mistake by buying a breaker smaller for this circuit. And yes, that will be caught during an inspection. For the non-continuous load below, I can buy the 20 amp breaker. I do not have to use that 125% increase. So this is why it's important to understand that. This is why I'm pointing it out, 3 hours or more. If you can already ingrain these things, when you get to the code sections where you're going to be going into deep math on this, you'll now understand the purpose of this 125 increase. It's so that now I can properly size a breaker correctly. If I have a continuous load versus a non-continuous load, I approach selecting the overcurrent protection device in 2 different ways. All right, let's go on to the next word, which is going to be all the way down in the D's, and it's one of the last ones because it has a W right after it, dwelling unit, and this is going to be way down in page 36. All right, way down in page 36. This one has 3 types because, and we should get to this one quickly, not too much to add to this. This is a family home, all right? Instead of them calling it a home or a residential, they call it a dwelling unit or a dwelling. So you have 1 family dwelling, you have 2 family dwelling, like a duplex, for example, or an apartment building, which they just label as multi-family dwelling. Bless you. And there's some specifics on it, right? And if you wanted to highlight that as well, I would also. The 1, the 2 dwelling units, and the 3 or more, right? Because it can come up, what is the definition of a multifamily dwelling unit? One that, again, a building that contains 3 or more dwelling units. Now, what is a dwelling unit? Don't forget this 4th one, because is a hotel a dwelling unit? Well, people sleep there. So let's look at the definition. A single unit providing complete and independent living facilities for 1 or more persons, including permanent provisions for living. And here's where a hotel becomes a hotel. Not a dwelling unit. A hotel or a motel or a Holiday Inn, these are not dwelling units because of the permanent part to it. So it has to have permanent provisions for living, sleeping, cooking, and of course sanitation, which, again, you do find in a hotel room or motel, which is, you have living, obviously, living room, sleeping, and cooking, but the permanent provision now becomes the non-qualifier for a hotel. All right, let's go to the next word, and we'll wrap up here in 9 minutes. I'll just move through these a little bit. You've seen me use the term now a few times because we do like to distinguish between on and off, because as I said, some things are on, some things are off, but some things start and stop. So we use these terms differently. Some things don't even do both of those. They just energize and de-energize, right? So like, let's say, for example, a heating element that heats up the water for a water heater. That's not starting and stopping. That's not on and off. That's energizing or de-energizing. All right, seems weird, because there are these little minor adjustments to these words, but that's what they mean. So the word electrically connected to or is a source of voltage. All right, and that's what energized, sorry, I didn't put the D there at the end, is. But there's another one. So let's say, for example, energized would be the breaker and the wire that is connected to the breaker, electrically connected to or is a source of voltage for that circuit. However, the metal box, the panel, where the breakers are sitting in, are considered likely to become energized. Conductive material, a piece of metal, that could become energized because of a failure of the electrical insulation or electrical spacing. So for example, if I'm taking off the wire or removing a wire from a circuit and I didn't shut off the breaker, and that wire happens to touch the piece of metal, Now that piece of metal is energized. That piece of metal is not considered energized, but that piece of metal that houses the wires, or the conduit, or the panel, or any real metal box that's in all this, or part of the electrical system, is considered likely to become energized. All right, so just so you understand that wording, because sometimes if you look at that and it says likely to become energized, when I was looking at this in my early days, I used to think this is something that should be energized. Like a light will likely become energized. Like this light is off, but it's likely to become energized when I flip the switch. But that's not how they're using that term, likely to become energized. They're talking about in the failure of an electrical system, things that are metal are conductive and they're going to energize. Things that are plastic are not. Right? You use sometimes plastic boxes in the homes for the outlets. Those things are plastic. They are not likely ever to become energized because they're plastic. They're non-conductive. All right, so two distinguishing words that we want to make sure that we are separating there. All right, and if there's any follow-up as I'm running over the next one, feel free to fire away. So far, so good. All right, we're jumping ahead a little bit. We're going to head over to page 41 where we're looking at garage. All right, there's, of course, different types of garages, not just for a house. There's industrial-style garages. All right, if you take your car to Pep Boys, that's a garage. So they're just the distinguishing feature for the three. So with this, I'm almost not too worried about anyone understanding this. You just come find the word garage and you can find the definitions for either one of those. But the main one, a building or portion of a building in which one or more. It's always that. That's a qualifier. Self-propelled vehicles can be kept for use, sale, storage, rental, repair, exhibition, or demonstration. So for example, if somebody were to, on the side of their house, put a little shed, right, and it has a door on it, that shed is not considered the garage. If they can fit a car into that, then it can be considered a garage. All right, so you have to be able to put an entire car. That's the definition. What is the definition of a garage? Is it just a little box on the side of the house or an area where there's a door? No, it specifically needs to be able to hold a vehicle. If it can hold a vehicle, then it's a garage. Now, a major repair garage, well, one where major repairs are happening, and a minor repair where minor things are happening. Distinguishing features, I don't think we have to go into those. Just as long as you understand the idea of the garage is, again, based off of a vehicle being able to go into that space. All right, let's go over to the next one, which is GFCI. And let's see here. Why didn't I see it? Oh, sorry about that. Oh, yeah, I don't see. Oh, there it is. Sorry about that. I was looking for GF. Sorry about that. Ground fault circuit interrupter. That's the entire name for it. And it'll be on page 42. And it's up here with right second one from the top left. A ground fault circuit interrupter, or GFCI, or by the way, we just call it GFI for the, in the field. The C is usually dropped because you don't need the circuit interrupter part, just that it's an interrupter. Is a device intended for the protection of personnel that functions to de-energize. So the antithesis, the other side of energize, is de-energize. A circuit or portion thereof, right, within an established period of time when a ground fault occurs. So first, let me just show a GFCI outlet, make sure everybody knows or has at least seen one, so you can look at the distinguishing factors that make up the GFCI. 1 second as this pulls up. So it's these outlets, right? It's not your regular standard outlet. It's this one here that has that reset, and it has the black one. If you can't see the letters there, it says test. All right, so you have a test and you have a reset button. In other words, you can come up to it and you can test to see if it's going to respond in the event of a ground fault, and I'll explain what that is. So you can hit the test to see if it shuts off, and then you can just simply reset it and let the outlet sit. Now this one, if you notice, has a little light or a little square right here. That's a light. It usually turns on green, I assume. I don't think I've seen one in yellow or anything. I think it's green. When you have power at the GFCI. So not only does it serve as an interrupter, shuts off the circuit in the event of a ground fault or a ground fault in the circuit, it also pretty much tells you when it's on and off. So that's a nice feature that it has on it. Some of them don't have that little light. You have to kind of pay for the better ones. Now, a ground fault. Let me explain what a ground fault is. Now, people use two terms when they talk about faults, and here's where we'll wrap things up. We'll remember that we ended at GFCI. There's two terms that we like to use. One is a short circuit, and one is a ground fault. Now, you'll notice this device is called a ground fault circuit interrupter. But oddly enough, it also trips in the event of a short circuit as well. So it trips in the event of a short circuit or a ground fault. Now, let me explain what these two words mean. They kind of mean two different things, but sort of one. This is why they're using the word ground fault and not ground fault and short circuit interrupter. I guess you wouldn't need the second circuit there. All right. In a panel, we have a wire called the grounding electrode conductor. All right, this wire goes to a ground rod, a piece of metal that gets buried, minimum of 8 feet, but the rod itself, when you buy it, is usually 10 feet. And so you drive it 8 feet into the dirt. This is in every house, building, or anything. You have to have this ground rod buried into the dirt. What this is going to do is, in the event of a fault where the neutral on a circuit becomes energized, this neutral at the panel is connected to this ground, and when the current finds its way onto the neutral, which is never supposed to happen, it can find its way out of the circuit and into ground. Now, let's bring a breaker into this. And now we have an outlet. All right, and we have our neutral. This is a circuit. All right, the reason this is a circuit is because the power is going into the receptacle, and whatever you plug into here will send the current out of the neutral. So we have resistance. All right, you guys did Ohm's law, so you remember what resistance is from the loads that we're plugging into this. And this is what keeps the hot and the neutral from really touching. Because if you, let's say for example, a light bulb, right? An old school light bulb style, where we had the filament, how we created light was one side of this filament was hot and the other side of that filament was neutral. So you had the hot and the neutral on the same piece of metal, but there was a lot of resistance on that piece of metal. So it would just get hot and create light. So the hot and the neutral are always working together on loads. The reason why we call it a short circuit is because the hot and the neutral touched, came into contact with each other. And so this is, again, going back, this is a circuit, and now when the hot and the neutral directly touch, it's a shortening of that circuit. Basically what you're doing is you're getting rid of the resistance now, and you're just touching hot to neutral. This is a short circuit. But let's say at that outlet, none of that happens. The hot and the neutral don't touch. Let me go this way. Sorry to bring back some stuff, but if not, I can. There we go. I have to erase and it can get messy. Let's say instead, remember we always have a ground everywhere. So we have a ground running to this outlet. And now let's say the hot and the ground touch. Well, how did the hot and the ground touch? I disconnected the hot wire from this outlet. I forgot to turn on the breaker, and it touched the metal where the box is sitting. I have now created a ground fault. All right, so simple terms. When the hot and the neutral touch, short circuit. When the hot and the ground touch, ground fault. Okay. At the load, over here. At the panel, it doesn't matter which ones are, because they all end up at the ground. So this is why they call it a ground fault, sort of as a overall cover to everything, because at the end of the day, everything is finding its way to ground. Whether the hot and the neutral touch, all right, hot neutral touched here, okay, but then what happened? Neutral to ground. Over here, the hot and the ground touch, okay, the ground got energized, but we're going to ground. So it's everything is really a ground fault, but when we're at the load, this is where we separate the terms as far as short circuit versus a ground fault. So this is why the GFCI takes care of all of it, short circuit or a ground fault. It'll respond, shuts off the circuit before the breaker has a chance to respond. Much quicker response time, about 0.5 seconds is what it takes for it to shut off that circuit. And that's what we'll pause it right there. I will stop the recording right here.